I'm still Olguin, a master's student here at the University of Wyoming. I am doing a video presentation on finding statistical differences in devices through leakage. This is done with PhD student Clay Carper under the advice of Dr. Mike Borowczak. This study begins with showing that we've only really done work on finding a problem. We've only just recently started this project at the beginning of this semester. Most of it has been us doing research. During this research, we found through a book from Randolph et al. That current method of analyzing leakage is only through three statistical methods, being the Pearson's Chi-square test, the Pearson's correlation coefficient, and Welch's t-test. These all are doing analysis on TVLA, or Test Vector Leakage Assessment. Test Vector Leakage Assessment is important because it tells whether a cryptographic device has any notable information about what operation it is performing to encrypt the data. As for the methods on what we will do with this project, it can be boiled down in simple terms that we'll generate a data set from different devices, and then we'll make hypothesis tests with different statistical methods to find any difference in means. The graph here on the right shows, well, this red data is consistently larger than the purple data for all the points we see. Because of this, we might look at the difference and see if there's any statistical difference through a hypothesis test. By contrast, looking at the red and blue data, because they intersect, it is very likely that they don't have a statistical difference. But if we had a larger sample size, it is possible that we will find more data to support the claim. One of the assumptions we make, especially for the Welch's t-test and the Pearson's Chi-square test, is that they work under a normal distribution. Now, the Pearson's correlation coefficient technically works under the same, but lots of data is required, so that is not a consequence. But if we have, as we learn in intro stats, many intro stats class, the central limit theorem states that if we have a large enough sample size, greater than 30, we can assume that our data is approximately normal through repeated sampling. So that issue gets fixed. Now I'll go over a quick review over the three different tests that have been identified by Randolph and Deal. The Pearson Chi-square test works primarily with categorical variables and with a high sample size. However, the central limit theorem helps with the high sample size by making it normal. That's the main requirement of a large sample size. And this figure on the right essentially shows what's going on. What we expect the variables to be is this top table with the E1, E2, E3, and E4. This bottom one is the O1, O2, O3, O4 are observed values. If we get a certain value of our chi-squared, the formula shown at the bottom, which is find the difference between our expectation and observed, we might find a statistical difference, at least one that is significant enough. Next, we have the Pearson's correlation coefficient. This is essentially finding the line of best fit. This is what correlation power analysis, which is a branch of side channel analysis, focuses on. It requires lots of test data to make a good line, and because of this, the normality of the data isn't as required because we will by default have a large sample size, which the central limit theorem helps with. Welch's t-test is a way of testing for differences in means. It is the most direct way that many intro stats and even just regular differences in means are implied. This is different from the student's t-test in the fact that we assume that the standard deviations and thereby their variances are different. By doing this, we make our hypothesis test, which is illustrated on here on the right. Our null hypothesis, or our basis, is showing that there is no difference. So when it comes to side channel, we will assume that our data is random. There is no significant predictor of what cryptographic operations are made. Whereas over here on the right, if we find that the null hypothesis is false, this is what we assume is that there is a difference. This mu1 and mu2 shows maybe perhaps mu1 is operations on our cryptographic device, whereas mu2 is just random noise to help obscure the leakage. As we are still in the beginning of our research, the current challenge is finding a good place to start generating data for our analysis. We don't know what exact devices we're going to use or what exact methods of observing the data, which is something that we are working on and will hopefully get figured out At least our current goal is by the end of this month of October. Now, depending on these results, we could generalize our results to find maybe some early samples could determine what type of encryption is being worked. As a result, we could do more specialized side channel attacks so that we don't have to do as many rounds to extract secret keys. And last, I have a reference to the Randolph and Deal book that really gave Clay and I inspiration for finding this research for this project. Well, that is our presentation. Thank you.